Got it. So you should see something on your screen that you have to say got it probably. All right. 1 second. Hello, YouTube. We're getting started here. Just a moment. And we're recording. So yes, go ahead.
All right, great. Well, thank you everybody for coming and out there in the virtual world. I'm going to introduce our speaker today, Esther Mullens, who is an assistant professor in the Department of Geography. Her bio indicates that she is an assistant professor in geography at the University of Florida. She received her degree in meteorology from the University of Reading, that's her bachelor's, and the University of Oklahoma for her PhD, followed by a postdoctoral appointment in applied climatology at the South Central Climate Adaptation Science Center. Her research is focused on various projects related to precipitating weather systems, their evolution and their variability and change in a warmer climate. Her PhD dissertation focused on ice storm evolution and thermodynamics in the southern plains, and more recent work has examined hydroclimate projections under climate change, precipitation variability, and operational flood forecasting. Dr. Mullens is a regional chapter author of the 4th National Climate Assessment. She enjoys translating science for broad audiences for extension purposes, I suspect. Do you have an appointment? No.
I am an extension appointment.
All right.
It was just part of my what I did with the former employer. Yeah.
Okay. That's obviously a challenge to communicate to that audience. And engaging with experts outside the academia who are plan to use climate data in their disciplines. She is one of a small team developing a new bachelor's program in meteorology at the University of Florida.
All right, well, hi everybody. Hello to those online. Good morning, afternoon, early morning, whatever time it is for you. So I, as mentioned there, I am a meteorologist / atmospheric scientist / climatologist, which obviously means that from the perspective of wetlands and water and watersheds, what I deal with is actually up in the sky, not so much what happens at the surface level. So this particular research that I'm working on here is from that perspective as a meteorologist. So as I mentioned, I would actually couch myself as a synoptic climatologist. So synoptic might be a somewhat unfamiliar term, but that just simply refers to a specific space and time scale in the atmosphere. And if you've ever experienced a winter storm or a big mid-latitude storm system or weather fronts passing through, something like that, that's all under the umbrella of synoptic weather. So I look at that sort of medium to large scale atmospheric and climate processes with that focus on precipitation as mentioned. So my research group primarily looks at, you can see I like puns, umbrella of topics related to precipitating weather systems. So ongoing and previous work has included ice storms, and that's both ongoing and previous, actually. I currently have a PhD student looking at ice storms in a warmer climate. Ice storms, by the way, look like this. They are when you have rain that freezes on contact with a surface. So you have a warm atmospheric layer above the ground, and then you have a very cold atmospheric layer at the ground surface. So while we never really get these in Florida, certain parts of the US can get extremely damaging forms of these events. But more broadly, drought, future climate projections, climate dynamics, weather systems analysis, so looking at how particular weather systems evolve in the present and future climate. And more recently, things like impacts and vulnerabilities, which is sort of leaning out into a world that I am a little less familiar with. So I'm going to give an overview of what I'm going to discuss today. I'm very happy to take questions, especially at the end, but if you're absolutely dying to ask one, then let me know. So I'm going to start with this idea of feast and famine. So this presentation is entitled Precipitation Whiplash. What is it and what causes it? So whiplash relates to this idea of rapid alternations between particular conditions. And in my case, it's between wet and dry. I'll then go on to explain the data, tools, and techniques, so all that technical stuff. Then a climatology of these whiplash events. So where do they occur across the United States? So I'm looking at CONUS, so the lower 48. looking spatially, temporally at these events, and then backing out a bit and looking at the role of atmospheric processes in creating these events. So if the first is just a basic climatology, the second is trying to get at what causes these whiplash states. Like, what is going on in the atmosphere? What is the circulation that's happening to create these conditions? And then finally, looking beyond that, ultimately trying to unpack where I hope some of this research is going to go.
Esther, just click on that. It says hide down there on that little screen on the
Oh,
bottom.
yes.
Just click on the hide.
Hide. There we go.
Thank you.
All right, so let's start with feast and famine. So the internet is full of wonderfully deep things, right? And here's an example. Sometimes you have too much of something, while other times you don't have enough. The internet says that. But it's true. It is our basic state of being, right? We have periods of boom and bust in our bank accounts, in just our lives, in just kind of our emotions. There are all kinds of things that go on, which means that we kind of go oscillate from one thing to the other. So this is fundamentally, this idea of whiplash in precipitating systems is natural. It can be augmented by various processes, including climate change. But there are obviously a spectrum of what you might expect. So in Florida, in the summer months, May is typically dry. June, we start to get wet when the summer sea breeze, thunderstorms kick in. But what happens if those transitions between plenty and lack, especially dry and wet, occur more frequently or with more intensity? So in other words, you're going dry, wet, or just more dramatic shifts between your dry month or season or year and your wet month, season or year. And so obviously, as an atmospheric scientist, I'm looking at this and thinking, this is a really interesting question in the atmosphere world. And it's also an interesting question, I think, for many sectors. In my work, in my previous employments, the professionals external to academia, so this would include things like farmers, water managers, engineers, would note that higher variability in weather or climate would be a more concerning scenario in a future climate, because it's less predictable. It's sort of it's different from what we would typically have expected in the past. But it also presents this idea of conflicting management decisions. So on the one hand, if you are told by a climate scientist to expect more precipitation in the future, that might trigger certain management strategies. If you're told you will have less in the future, that triggers another set. Now, what if you have both? And depending on how frequent or how dramatic that is, that can lead to some difficulty in preparing for that. So the reason that I became interested in this also goes back to where I used to be. So I was a PhD student and then a postdoc at the University of Oklahoma, which is in Norman, Oklahoma, also known as Weather World. It's like Disney World for meteorologists because there's so much happening there with the National Weather Center. And during my time there, I, of course, was just existing in that climate. And I lived in Oklahoma between 2010 and 2015. So I'm going to tell you kind of a story of what went on in a very broad sense over that 6-year period. And I do that through looking at what's called the Palmer Drought Severity Index. So it just gives us a sense of, over sort of a seasonal time period, how unusually wet or dry areas have been. Here it's broken down by climate divisions across the CONUS region. And so you can see in July of 2010, pretty wet across the northern plains, pretty average across the southern plains. And just focus your attention mostly on the plains. And I'm just stepping forward a year. Obviously, these scales can differ, but to illustrate, if 2010 was a pretty standard year, 2011, we were in this massive drought and we had a huge heat wave. Those two things tend to occur simultaneously in the plains. Of course, up here it's still quite wet, so you have this huge dipole between the southern plains and the northern plains. Go to the next year, and the drought persists. It's extended further into the west. So now the area that was wet is now dry. The drought persists over time, but eventually ameliorates down in the southern plains before 2015, which represented one of the wettest springs that we ever have had in southern Great Plains. So if you go from this situation and just a few years later this situation, this part of the country is already a highly variable region, in part because you are sitting at the boundary between the very moist kind of east zone and the arid west, and so there's always sort of a bit of a push and pull of where the rainfall is going to be in a given year. But as you can see, just being in that place, I was fascinated by how our sort of pluvials and droughts would vary. The Great Plains is a region that has a lot of billion-dollar disasters. In this case, over that same 5-year period, it was top 5 for total damages and top 3 for per event damages, with one of the largest being drought, and then flooding and severe storms. And severe storms and flooding tend to be linked to the same types of weather systems produce both. So the research questions that I'm pursuing, what are the geospatial frequencies and magnitudes of whiplash? And I will define whiplash in a minute. And what is their seasonality, if they have any at all? Are there specific trends in whiplash frequency or magnitudes with time? So are we experience more, less, about the same? How are whiplash events driven by the large-scale environment? So this is where I get very meteorological on you all, so just be prepared for that. And then finally, is there any chance that whiplash events are predictable at seasonal to sub-seasonal timescales? So in other words, can we find some predictability in these that potentially could be of use for seasonal forecasting? So here's the definition of whiplash. And I include this just to show you that we actually experienced a whiplash event earlier this year. So February, really dry. Up here in Gainesville, we got somewhere between 25 to 50% normal during that month, followed another previous dry months. We're in a La Nina year, so it tends to be drier. And then in March, we just got dumped on by rain. And so that is the illustrative example for this year. So there's actually limited published research on precipitation swings. What tends to be more prevalent in the literature is just looking more generally at variability. So either you look statistically at things like standard deviations over time, or just other types of statistical criteria. In this case, what is different about whiplash is that it's actually temporal sequences rather than just generically changes in variability. So there have been a few papers on this. One example used shifts between Palmer drought severity indices between moderately wet and moderately dry over a period of about a year, I think. So they were looking at year-to-year whiplash. This was also true of another paper where drought years either immediately preceded or succeeded a wet year. So similar definition, looking more at the annual totals and how those vary between years. And then another more recent work, annual precipitation accumulation falling below the 30th percentile in 1 year and exceeding it in the next, or vice versa. And then a fellow colleague has brought that down more to a season and to season or month to month, where 1 month falls below the 25th percentile, the next above the 75th, and these are based on historical climatologies of the monthly average precipitation, and that can be in either direction, right? So you have either a dry followed by a wet couple of months, and then or you have a wet followed by a dry. Ultimately, I kind of went with that. I decided to look at month-to-month variability. However, the same logic can be applied to season and annual to annual. And using that same threshold, So a dry month would be considered as a month that receives less than or equal to the 25th percentile of what is typical for that month, based on a baseline of 1981 to 2010. The wet month would have to have monthly total accumulated precipitation at or above the 75th percentile. So essentially kind of lower quartile, upper quartile. So with that definition, now let's see, okay, so I've begun to kind of work through some methodology. So first off, I'm studying the continental US, and I'm using the subdomains analogous to the 7 regions used in the National Climate System. So whilst the data I'm using is gridded, so in other words, you get grid points across the whole region, I am aggregating certain statistics over specific subregions of the country that is generally consistent. I don't quite use the state boundaries. I use kind of more of a lat-long, so there's kind of fuzzy boundaries between some of these regions. But ultimately, the idea is to capture the differences across the country because it's such a vast country. Now, obviously, from the perspective of more local changes, that seems incredibly broad. But that sort of is necessary given the scale of the type of work that I'm doing at this stage. Certainly, these same things can be boiled down to counties, regions, but right now I'm looking countrywide. So the first thing is I need a long data set, partly because in order to really understand, to get an adequate sample of these types of events, given that I'm looking at month to month, there are 12 months in 1 year. So I want to have a decently long sample of years in order to really kind of understand what's going on. So there is a data set called the NOAA 20th Century Reanalysis version 3, there are 2 other versions, which is a meteorological data set that uses a model as well as assimilates sea level pressure observations going way back, in order to create a fairly consistent long duration data set for meteorological variables like moisture, atmospheric dynamics, and it has its own precipitation in there, but I actually use observations. Although they have been modified, they are from the Global Precipitation Climatology project, which is, in this case, I use a 1/2 degree by 1/2 degree latitude and longitude. And this is monthly precipitation over land surfaces. That is available from 1891 to 2016. So 0.5 by 0.5 is fairly coarse resolution, but again, the ultimate aim here is to look more at those sort of this broad sense of what whiplash looks like across these subregions and the country at large. And there is always a compromise between high resolution, shorter term data and lower resolution, longer term data. And so in this case, I go for the longer. And so I ended up having a matched data set between 1891 and 2015. So that's about 125 years. So I have that data, but then I want to try and remove whiplash events that are occurring on small scales. So if you think about it in a sort of real world example, it could be that here in Gainesville 1 month, we just miss all the thunderstorms and we just don't get much rain. But then the next month we get all the thunderstorms and so we get a lot of rain. And so that scale is pretty small. It's somewhat random and it's not typically driven by any sort of large scale weather system. And so I create a minimum size for these whiplash events. So in other words, a month-to-month transition, one whiplash, also has to meet a minimum spatial criteria. So there has to be a certain number of grid points that experienced that whiplash event in order to remove these less predictable small-scale things. Okay. So here's an example of what a single whiplash event might look like in the data. So 1976. This is April to May, so I have it reversed. So it comes up as April's the dry month, and May is the wet month. And so this is the spatial distribution of that whiplash event, essentially, like all of the grid points in which it was satisfied, there was a whiplash event. And then here is the magnitude variation, again, it's kind of blocky given the resolution. Here is, so this one actually represents one of the top 20th percentile in terms of spatial area. So it's a larger scale whiplash across a broader domain. And in this case, this is more of an average size event. Okay, so to recap, data, 2 data sets. One that I'll bring in later on, but all the things you just saw with the precipitation itself is from the GPCC. I come up with 2 definitions of whiplash, and I actually treat them somewhat independently at the moment. And that is to look at events that are dry to wet. So the first month is dry, the next is wet. And then wet to dry being the opposite. So I actually split these 2 up. Now, I'm not, they might occur at similar times of the year, at similar spaces. We'll see whether or not that's true later on. And then 2 metrics that come out of those. Frequency, so that would be the number of whiplash cases per grid point or region, analyzed over, annually, annual totals, monthly totals over a given year range, seasonal, that sort of thing. And then magnitude, so that would be the difference in the accumulation between the end month and the beginning month. So that's in millimeters. So basically, like, what was the actual change in precip that occurred between those 2 months. And so the outputs then is basically I have this data set that now spans the whole CONUS, that has these frequencies and magnitudes, and I can start slicing and dicing them into various different statistics. Now, obviously, there are limitations. The long duration, as mentioned, compromises spatial resolution, so I am looking broadly rather than in a small scale. GPCC is based on surface precipitation information, so it's primarily rain gauge based, and they use these interpolation techniques to create a grid out of that data. However, if you look with time, obviously the number of rain gauge observations changes, and it increases the closer to the present day you get. So that's something to consider, is that you obviously have less information in the early period and more in the later. And so any trend that you get out of this data should be interpreted with some degree of caution. Another caveat, sort of more with the outcomes of this experiment, is it's unclear what practical implications this high month-to-month variability has. And so there's more explanation, it might not be me, it could be all, could be someone else who wants to look into, just these whiplashes, what do they actually do at the surface, right? Because at least here in Gainesville area, February was bad, we were in a drought, and that drought was removed in March because of the deluge, right? But there are other impacts, shorter term impacts that could occur, like flooding and other sorts of things with the sudden input of water. The other caveat is that whiplash events are usually associated with just 1 or 2 anomalous weather systems. So over a 6-month period, let's say, 80 to 90% of whiplash events occur between 3 of those months. So about half of the time you have some sort of change, and 40 to 60% represent 1 event. So only out of those 6 months, 1 had this transition. It was just a large event. So it's oftentimes the size, the spatial dimension of these that really drives the frequency statistics. Because I look at the total number of whiplashes across space as well. So in some cases, we just have to recognize we're looking at perhaps 1 or 2 really anomalous situations, not like a state that's ongoing the entire time. Different definitions may yield differences in the findings, and that I apply this month to month with calendar months rather than some sort of running average. Obviously, weather does not adhere to our calendar month system necessarily, and you could have very dry 30 days and a very wet 30 days, but in this case, I'm kind of tying it to our definitions of months. All right, so let's talk a little bit about some of those results with the climatology aspects. This is the sort of spatial and temporal work. And I'm actually going to eventually boil this down to looking at two very specific domains, which is the southwest and the southeast. Really just picking out southeast because that's where we are, and the southwest because it represents a different climate to us. So here is the spatial distribution of dry to wet counts. This is the total counts over that period of time, and the wet to dry counts again expressed as total frequency. And so all the subdomains are shown here. And so what you can see is really just, first off, they both look fairly similar, right? So that tells me that where you get more of these transitions in wet to dry, you also get a similar thing with the dry to wet. There's not really an area that highlights itself as sort of, you know, like a whole domain that highlights itself as being very distinctly different. Now, obviously, there are locations. And some of these locations, for example, in Desert Southwest, you can actually, this area is semi-arid as well, got the mountains here. And so you can kind of see and pinpoint some things. I mean, down here, maybe this little max here is because we have that very abrupt onset and cessation of the sea breeze season. Now, magnitude, if I were to just do magnitudes based on the absolute magnitudes, it would also look fairly similar, I think, across the way. It actually would look smaller over here. So what I ended up doing is expressing the magnitude between the wet or dry month and vice versa. This is the absolute magnitude as the fraction of the median annual precipitation in that location. So in other words, just like how kind of important is this sort of, particularly the pluvial element, the wet element, to the annual amount of precip. And so you can clearly then begin to see how you know, this variability is important in these semi-arid areas, which don't get a whole lot of precipitation. And so you are just seeing how important these heavier precip events are to the hydroclimate of those locations. The next thing is to look at this from across a year. So essentially to take the frequency, so the mean number per grid point in each month, to get a sense of, okay, do these occur at particular times more frequently than other times? And what's shown here is you can see these are the two regions I'm looking at, the southwest and the southeast. What you'll see is the dry to wet transitions are shown by the blue bar chart, and the red one is the wet to dry, and those green lines denote the monthly average total precipitation. So what you can immediately see is, again, there's no dramatic seasonality that is occurring here. It might be that there is some degree of increased frequency here in the May to June timeframe, which in my mind is definitely associated with the onset of the southwest monsoon in that part of the country. Over here, again, not much to say there's any particular seasonality, but perhaps a little bit more in one month or the other, but it's not terribly dramatic. Now, if I switch to magnitudes, and these bars represent the amount as a fraction of the onset month's precipitation. So once again here, you see the green is the average monthly precipitation amounts. The dotted lines here represent the absolute magnitude, so the actual magnitude not expressed as some relative change based on the time of year it's occurring. And you can now really pick out the southwest monsoon months. So for context, that occurs during usually June, July, August, and that is when the southwest region gets a little bit of an uptick in their rainfall. Now, during the winter months, that's actually their peak. They get the most of their precip during the winter months. And so you can kind of see that whilst the actual magnitude changes reflect that seasonality in the typical accumulations, the relative really highlights the months that are associated with the southwest monsoon. The same is actually true here, and the cessation of the monsoon is usually during this period, which also shows an uptick. That actually goes off the chart, and this is the relative fraction rate. So in terms of the change, this could be over 10 times the magnitude of the onset month's average precip, so it'd be quite extreme. In the southeast, the only real obvious thing here is that dry to wet kind of peaks perhaps a little ahead of the summer and perhaps into the winter months, and here it's kind of more obvious that this would represent the end point of the summer rains. And so in some cases, what you see really is an enhancement of kind of the traditional seasonality of precipitation. Variations in time, and this is for the southwest, the top is magnitudes and the bottom is frequencies. The axis is a little confusing because it's basically millimeters per grid point in the top one weighted by domain size, and this is total number per grid point weighted by domain size. In order to put them all on the same scale, essentially, or similar scale. The dashes are just the interquartile range there. So what you can really kind of see is that there looks like there's some sort of cyclical behavior. I mean, but it's so, I mean, when I'm looking at it, I'm like, yeah, I probably should like have a closer look at that. There's not an obvious, to me, sign that magnitudes are increasing in time or frequencies are increasing in time for the southwest. But there is relatively high variability between years. The southeast, similar results. There's clearly high year-to-year variability, but not necessarily a pronounced trend. Another quick exploration. Do these whiplashes, like wet to dry or dry to wet, really, do they have a relationship with the total annual precipitation? So in other words, in years in which you get more of these, is that there greater amounts of precipitation or less? Turns out in most cases it's greater amounts, even if it was a wet to dry transition or dry to wet, doesn't matter, especially for the Midwest, Southern Plains, and Northern Plains, so the interior parts of the country. In the other areas, there are weaker relationships, still mostly positive. The Southwest is interesting because unlike some of the other regions, it has a dramatic difference in the correlation, where actually there is a correlation, a positive relationship between total annual precip and the wet to dry regimes, but not with the dry to wet. This one was another sort of a little bit of a general check on the data, just how much of a relationship is there in between the different regions from each other and the dry to wet and wet to dry. And so whilst I'm not really going to explain any sort of, well, I don't even really know what to say. There are some areas that show relationships and some not, but you can clearly see that down this diagonal here, basically the wet to dry and dry to wet show strong correlations. In other words, for the most part, a year period of time with greater wet to dry events is going to also have greater dry to wet events. So there's something going on with the atmosphere that's driving these anomalies. That also seems to maximize in the plain states. And it's weakest in the northwest and southeast. Okay, so in terms of what has come out of that is that frequencies of whiplash are fairly similar across the CONUS, but magnitudes show some increase. Relative magnitudes show increase in the central and western US. Seasonality of whiplash is often linked to climatological transitions, so it's in many cases an enhancement of an existing transition. So if you have a typically dry month and then a change to a typically wet month, this could represent an enhancement of that type of thing. Frequencies of events do not really show a whole lot in terms of trends that you could describe to climate change necessarily, but they do show high interannual and interfluid variability. There's a high correlation between wet and dry and wet events. So this idea of sequences of climatic anomalies is important. All right, so the role of atmospheric dynamics. What I mean by atmospheric dynamics, so I don't know whether this is really going to work or not, but let's see. If any of you have ever seen Earth Null School, this is kind of a fun look. This is based on a weather forecast model. But if I show you basically near the North Pole, you see that the atmosphere it's wavy, always wavy. Especially so in the higher latitudes. And the magnitude of those waves is pretty critical for weather systems at the surface. So what you might be able to see currently right now is that the flow over North America is mostly west to east, which represents what we would call zonal flow, which tends not to lead to much in the way of extremes. It's pretty average. However, if you go to an area where you see these winds dipping down and moving up, this wave activity suggests that there is kind of more dynamical things happening. There's warmer air getting pushed up here into Western Europe, and there's colder air getting dragged down here into the Atlantic. And so that often is the site for the development of weather systems and severe weather. So waves are critical, and basically atmospheric dynamics is the study of waves and how they transport various key quantities around. What I showed you there, the larger waves are an example of Rossby waves. So these are atmospheric long waves which transfer heat from the tropics to the poles. They drive development of storm systems, and they're associated with upland jet streams. So their movement can vary. If those waves are moving slowly and they're highly amplified, they can produce more dramatic weather. For example, heat waves, cold waves, flooding. Faster motion in those waves suggests more short-term variations in weather, but overall perhaps less sort of intense changes. So amplitude is important. My hypothesis moving forward when it comes to why we get these whiplash events is that they're related to flow reversals and atmospheric circulation. So in other words, they're related to an amplified atmosphere where you have, over some period of time, anomalous, northward movement of air, ridging is what we call that, and it's like very hot and dry, and then you might over time get the reverse situation, and then back again. So starting with this idea of Rossby waves. So let's imagine that we have a wave that looks like this in the atmosphere. And those warm blobs, the red blobs represent warm, kind of dry conditions, an atmospheric ridge, high pressure. And the blue represents kind of low pressure, which is more stormy, wet, that sort of thing. And the movement of these is typically west to east because we're looking here at mid-latitude conditions for the most part. There is something called the Rossby phase speed, which is denoted by this equation over here, which essentially looks at the mean flow in the atmosphere from west to east, and then gives a sense of, which is related, well, the Rossby phase speed is directly related here to, and this is the wavelength. This is related to the amplitude, and then you've got 4 pi squared, which is constant. And so if I plug some numbers in that represent traditional mid-latitude atmosphere, the movement of this wave is about 5 meters per second. Now, if I look at a high amplitude wave, so in this case, the wave amplitude has now gone up by about a factor of 3. It's still going to be pulled along by the prevailing west to east flow. The amplitude is higher, so you would expect to see more anomalous warm and cool and wet and dry conditions. If I plug some numbers into that, now I actually get a westward moving Rossby wave packet, which in other words actually means that there is a slowing of the progression of this. Instead of carrying along with the flow, it's actually acting against the flow. And so it slows down. And so if you imagine high amplitude slows down, that creates more conditions for extremes. I'm now going to look at this from the perspective of 2 seasons, the warm and the cool season. I take what's called geopotential height, which is a measure essentially of the kind of anomalies in atmospheric wave behavior, and I convert those into a standardized anomaly. And I also take the zonal wind, which is the west-east wind, the meridional wind, the south to north. I look at those wind vectors at 700 millibars, which is a little closer to the surface. It tends to be the zone where you might pick up moisture and move it around, that kind of thing. I then actually regress, so I have that data, and I regress it at each grid point against the time series of Whiplash. Well, so the time series of Whiplash in a particular domain. So if I'm interested in the southeast, I look at this. I take the southeast Whiplash time series, and I regress the height field. So I'm looking really, what's the height field doing when that region as a whole is experiencing more or less of these events? And what I get is something like this. So remember, the atmosphere is just composed of lots of different waves, and this is anomalies. So where it's blue, that means you've got like a lower height, cooler air or stormier. And where it's red, you've got like a high, so it's usually a ridge. It's typically warmer and drier. And so in these transitions between dry to wet events or wet to dry events, and so that's southwest, dry, wet, wet, dry, dry, wet, wet, dry. There's some interesting features that kind of come out. So dry to wet, for example, and this is the summer, so this is the warm season. This high pressure is the monsoon high. And it's suggestive here that during dry to wet transitions in that area, the monsoon high is stronger. And what happens is as it moves north, it drags in a lot of moisture. So a stronger and more persistent high would likely bring more moisture in eventually, right? So it would start off being very dry, but as it moves, it would bring enhanced moisture into the area. The wet to dry suggests that the flow is generally more in the way of troughing, so that would initially produce wetter conditions, but we also then we get more of this flow off of the cooler northern waters into the southwest, which might also suggest that we're cutting off moisture into that area. This, interestingly, down here suggests a stronger trough that is often associated actually with the cessation of the sea breeze. This usually occurs in the autumn. Our first cold front cuts the sea breeze off and it ends. So that suggests that it might be an enhancement of that situation towards the end of the warm season. In the cool season, these anomalies tend to be stronger just because that's the time of year where you get more enhanced dynamics. But the signatures are different because there's different mechanisms operating during that time of the year. It's the wettest season in the southwest, and it's the drier season in the southeast. Now, I'm not going to go into too much depth right now, but there's an interesting clue based on these particular features for the southeast. And the southwest, again, just shows flow reversals to some extent in the wind fields, as well as you can kind of see this highly amplified behavior of the flow, at least in this one, not so much in this one. Okay, so the next thing I'm going to do is even more crazy and complicated, is this thing called Rossby wave activity flux. So now I want to look at the movement of waves over time, but without actually making tons of GIF videos that show the movement of waves over time. So this wave activity flux is actually, it kind of tells me, like, are these Rossby waves moving faster or slower? Are they likely to grow larger or weaken, that sort of thing. So I realize I'm definitely probably going a little bit over time. So what I'll do is I'll just kind of move through this fairly quickly. If you're interested in how this works, I have a slide later on, but basically I filter the data now. So the data that goes into this is daily. I filter it to a 7-day timescale to basically remove any high frequency changes in the height field which are associated with non-synoptic weather. So I just want to keep the large scale. I create running averages from that. And then I use the equations of the Rossby wave flux to back out the wave flux activity in the zonal and radial directions, which I can then create a vector out of. And so this is kind of how to read it. So for the next slide, what you'll see is wave activity flux anomalies. And so eastward anomalies suggest that the flow is faster moving to the east, more progressive, but that it can amplify the upstream, so it can actually keep creating larger waves on the back end. Westward anomalies slow down the flow, and they actually amplify the downstream. So what that is like, practically speaking, is if you all were to exit there and the first person that goes through the door drops their phone and stops, and then everybody crashes into them. So that's kind of what's happening with the westward anomaly, right? So it's actually creating kind of a block, and then everything else is amplifying on the rear side. I'm going to not talk too much about convergence and divergence, but the same thing, looking at warm seasons and cool seasons. And so what you see here, so these dark arrows represent significant wave activity flux differences. Again, this is a regression. And so in this case, this is a westward anomaly, suggests that in the case of the summer monsoon circulation, it is slowing down and potentially amplifying based on the direction of those fluxes. For the southeast, for the dry to wet, we actually have more progressive flow, and there's lots of actually wave convergence here, which can sometimes lead to the breaking, what we call wave breaking, which can create these kind of anomalous conditions that can lead to kind of more aggravated weather, you could say. What's interesting is these two actually look very similar, and I'm not quite sure why that is yet, but obviously the southwest and the southeast are linked by the zonal flow that goes from west to east, so there's something happening there that is worthy of exploration. In the cool season, there are significant wave flux anomalies in the southwest, in most cases moving in the westward direction. So again, if you imagine, that just kind of holds everything, that builds stuff to the east, amplifies conditions further back, as well as slows the movement of the overall system. So you can kind of think of it as the pattern just kind of gets stuck or it amplifies. The southeast actually shows basically no significant difference in wave activity fluxes. However, it still shows you these anomalies, which, spoiler alert, are associated with the negative phase of the El Nino Southern Oscillation, so La Nina. I'm going to skip through this a little bit, because I've kind of explained a lot of that. And just finally, links to planetary scale variability. I did highlight that some of these signatures are suggestive that there are known modes of variability occurring. And when I mean known modes, I'm talking about things like El Nino Southern Oscillation, Pacific Decadal Oscillation. These are all large-scale atmospheric teleconnections that occur at fairly regular intervals and drive a lot of anomalous conditions across the globe. So if you do a wavelet analysis of the southwest and southeast annual time series, there are some lower frequency periods that come out here on the 16 to 32 and even greater year timescale. So the contenders at that point could be the El Nino or La Nina, which again creates anomalous circulation across the country, PDO, which does similar to El Nino and La Nina, just at longer timescales. And then this thing called the Atlantic Meridional Oscillation, Atlantic Decadal Oscillation, sorry, which is a much slower variation between warmer than usual Atlantic sea surface temperatures and cooler than usual. And so I basically go through and I run running correlations between the 10-year running mean of these Whiplash events and the running mean of the teleconnection pattern. And so you can see that there's variability over time. It's not kind of like, oh, great, it's definitely always this way or that way, it changes. Same with the PDO and the AMO, right? So when you actually just look at the base level teleconnection and correlate it with a smoothed version of the Whiplash time series, in this case, just dry to wet, then you see things coming up here. But what was more fascinating is when I actually took then the correlation, the running correlation of the teleconnection with the smooth whiplash cases, and then I correlated against another teleconnection. So at this point, I'm looking at compound teleconnections. And in this case, the AMO. So I correlate all of these things, the ENSO with whiplash time series against the AMO, and I find these dramatically strong negative relationships in the southeast, which is the blue highlighted there. The southwest is a little bit trickier in terms of what's going on. I'm going to skip the PDO and ENSO for now because they didn't have as obvious signatures. But what I will say, and what I think is definitely interesting for this region, is that the AMO modulates the role of ENSO on these events. So during positive AMO, which is warmer temperatures in the Atlantic Ocean, La Nina is linked to higher frequencies of whiplash events in the southeast. During the cool AMO, it is El Nino. So there's something happening there that's kind of interesting and potentially predictable. But the southwest region's a little bit more complicated, tends to be linked more to the Pacific, which is fair enough because that is its nearest ocean. So in terms of concluding thoughts, this stuff is all things that I've looked at. You can ask me again in a minute, but where am I going? So on the one prong, I've done climatology, on the other, atmospheric circulation, and the third, teleconnections. And so all of this is really just trying to get at, what is the predictability or potential predictability of whiplash events? And perhaps further work beyond that is just what is the impact of these events? What kind of hazards do they produce based on the data information we have, or case studies of specific events? And so those three prongs, hopefully over time, will get a better handle on what's happening with the atmospheric dynamics, the links to the large scale, and obviously just growing our understanding of how whiplash events vary across the region. All right, sorry I went a bit long.
That's great. Everybody, a hand of applause for Dr. Mullens. If you have to go, please do so. Otherwise, any questions in the room?
Yes.
What's the expectation for the Rossby waves in the future? I mean, you didn't see, it's amazing how that greater amplitude really starts to change the rates of that. So is there a prediction that those are going to become more amplified or less, or we don't know yet?
There is some indication that they could amplify. They tend to be more undulatory and slower moving when the temperature gradient between equator and pole is less. And since that's likely with a changing climate, it's anticipated that that will potentially drive larger anomalies, which in itself then can drive these sort of, what we've seen actually in recent years is eastern floods, western drought.
Right.
It's typically a massive wave where you've got a trough, lower pressure in the east and high pressure in the west. So there are some people working on that, for sure, trying to see what's likely to be the case with wave behavior in the future.
Professor, I have a quick question on it. In slide 19, there is this graph, versus annual precipitation for southeast.
Slide 19?
Yes, slide 19.
Is this one?
Yes, I think the next slide, I believe. So
okay. Yeah.
So here you consider annual precipitation, right? Is this annual precipitation?
The green line is monthly average.
Are you considering all type of precipitation or just the whiplash?
So in this, in the green line, it's all types. It's just merely there to show you what the typical climatology of precip is like versus the whiplash events themselves.
Yeah.
Okay.
David, do you have anything online? Questions?
The YouTube is characteristically very quiet, but had viewers on there. So I guess a general question is, you obviously use modeled data and as well as tons of observations to try to get these statistical phenomena. And I'm wondering if you find that, like, the statistical approach or the sort of mechanistic modeling approach, if one has a sort of advantage in predicting what's going to occur in the future.
So, in terms of so that would be, if I'm understanding you, those two types of modeling are largely, I'm thinking of it in the context of seasonal forecasting. Or sub-seasonal forecasting, so that's like the 3-week to 3-month time period. Climate change with this sort of stuff, if I were to look at this with climate futures, I would be using climate models, and I would be kind of extracting from their time series some of these similar statistics. From the predictability angle, you could try and build a statistical model based on the findings here. For example, this link between AMO, ENSO, and the Southeast Whiplash. However, obviously there's a lot more to it than that. And then the dynamical, there are dynamical seasonal models that are available currently, and another angle could be to sort of evaluate their seasonal forecasts of whiplash and whether or not they're actually verifying, whether they're capturing the types of things that are associated with these events. So I could see a number of angles in terms of the use of models for both seasonal predictability and climate predictions.
Great,
I don't know whether that answered your question, but it's like.
Thanks a lot.
Is that it, David?
Yeah, no other questions here from Zoom land or YouTube. So just thank Dr. Mullens again and appreciate you coming to give the seminar this week.
Hey, thank you.
So, Esther, while you have that up, you had that, there's one about the density of wave or rain gauges.